Okay, so get this. We're talking about an algorithm that can predict things like house prices.
Yeah.
Like way faster than you can say location, location, location.
Yeah.
It's linear regression. And in this deep dive, we're going to break down how it works, how to actually use it, and just how powerful this tool can be.
It really is remarkable how widely used linear regression is. I mean, you see it in everything from finance to healthcare.
Oh yeah, for sure.
All because of its speed and its ability to just give us clear, interpretable results.
So we're diving into a couple of sources today.
Okay.
One from Exponent about machine learning engineer interviews, and another that's a deep dive into linear regression itself. And let me tell you, they are packed with insights.
Absolutely.
So first things first,
Yeah,
linear regression, it's all about prediction.
it is.
So imagine you're trying to like guess the price of a used car.
Okay.
You'd probably consider like the age of the car,
Oh, yeah.
the mileage,
You-
make and model the condition.
Yep. Those are like the data points that would help you make a guess. And linear regression does something similar, but it makes it a science.
Okay.
It takes those features
Yeah.
and it figures out how much each one contributes to the final price.
Interesting.
It's like having a formula that spits out a prediction based on those features.
So like a weighted average where like
Yeah.
some features matter more than others.
You got it.
Got it.
And the really cool part is how the algorithm actually learns those weights.
Yeah.
It's kind of like showing a kid flashcards with car features on one side
Yeah.
and their prices on the other. And the more flashcards they see, the better they get at just guessing the price of a new car based on its features.
So it's learning from examples just like we humans do.
Exactly.
Now, the Exponent Guide mentioned that this type of learning is called supervised learning,
Yes.
where we give the algorithm labeled data to train on.
Right. And the algorithm starts with a very simple linear equation.
Okay.
It basically multiplies each feature by a weight, adds them all up, and boom, you get a prediction.
But like, how does it figure out the best weights for each feature?
So that's where things get really interesting. The algorithm starts with random weights,
Okay.
and then it makes some predictions, and it compares those predictions to the actual values.
Okay.
And the bigger the difference, the more it adjusts those weights to try and get closer.
So it's like a game of hot and cold.
Yes.
But instead of, saying warmer or colder,
Yeah.
it's adjusting those weights to zero in on the best prediction.
Exactly. It's constantly tweaking those weights
Okay.
to get closer and closer to those actual values.
Yep.
And this process is called gradient descent.
Interesting.
You can think of it like trying to find the lowest point in a valley. Each tweak of the weights is like taking a step downhill until you reach the bottom where that error is the smallest.
I got it.
Good.
Now, the guide also mentioned that this algorithm can handle like tons of data,
Oh, absolutely.
like way more than like a human could ever process.
Yeah, for small data sets, you can use linear algebra to find the best weights directly. But when you're dealing with massive amounts of data, we use this iterative approach, adjusting those weights bit by bit with each chunk of data.
That makes sense.
Yeah.
Now, I remember reading something about regularization in the linear regression deep dive.
Yes.
What's that all about?
Regularization is a way to keep our model from getting too excited about any single feature.
Okay.
You see, sometimes a model can get so focused on the training data that it starts to memorize those specific examples
Okay.
instead of learning those general patterns.
So like a friend who aces the practice test by memorizing all the answers,
Yes,
but totally bombs the real exam because they didn't actually like learn the material.
that's a perfect analogy. That's
Yeah.
what we call overfitting.
Right.
And regularization is how we prevent it.
Okay.
It's like adding a little bit of a penalty for using overly complex weights. This helps the model stay more balanced and generalize better to new data it hasn't seen before.
So it's like making sure that the model doesn't become a one-trick pony.
Precisely. And there are a couple of popular flavors of regularization ridge and lasso regression.
Ooh, tell me more.
So ridge regression is like a gentle nudge.
Okay.
It shrinks all the weights a little bit to prevent anyone from getting too large. It's like saying, hey, let's not get carried away with any single feature.
And lasso regression is a bit more dramatic.
You could say that it's like a sculptor chiseling away at the weights.
Okay.
Forcing some of them to become zero, this ends up with a simpler model that uses fewer features. It's like saying only the most important features get to stay.
So ridge is about balance,
Yes.
and lasso is about simplifying and picking out the MVPs of the features.
That's a great way to put it. Now, let's talk about how we actually make this magic happen in code.
Okay.
The exponent guide gives us some Python examples using libraries like scikit-learn.
Scikit-learn. It's like the superhero of machine learning libraries in Python. You just feed it your data, tell it what kind of model you want.
Okay.
It's like Ridge Lasso or plain old linear regression, and it just does the rest.
It handles all the heavy lifting,
I love it.
making it incredibly easy to implement these models. The guide also mentions stats models, another Python library
Okay.
that's popular with people from more traditional statistics backgrounds.
Right, like those who love their t-tests and p-values.
Exactly. Stats models gives you a bit more in-depth statistical analysis alongside the model results.
Okay.
So it's a great choice for those who want to really dig into the numbers.
So we've got our tools and we know the basics. But
Yes.
before we get too excited,
Yeah.
our sources emphasize that we need to make sure our data actually plays nicely with linear regression's assumptions.
Yes, the assumptions. These are like the ground rules.
Okay.
For our model to work its magic things like linearity,
Meaning that there should be a straight line relationship between our features and what we're trying to predict.
precisely if the relationship is curvy or all over the place, linear regression might not be the best fit.
And then there's normality of residuals. It sounds complicated.
Right.
What does that even mean?
It's actually pretty simple. Residuals are just the differences between our predictions and the actual values.
Okay.
Normality of residuals means that those differences should follow a bell-shaped curve.
Okay.
Like if we're predicting house prices, most of our predictions should be pretty close to the actual prices, with fewer predictions being way off.
Yeah, so most of our errors should be small and clustered around 0,
Exactly.
with fewer large errors. Like if you're playing darts,
Yeah.
most of your darts should be clustered around the bullseye, with fewer darts way off target.
Exactly. And then there's non-collinearity. Our features shouldn't be too buddy-buddy,
Okay.
meaning highly correlated with each other. It's like having two witnesses who tell the exact same story. It doesn't give us any new information and can actually mess things up.
Right. We want our features to be telling us different things about the outcome, not just repeating the same story.
Exactly. What else do we need to watch out for?
Oh, well, there's homoscedasticity.
Which is a fancy way of saying that the spread of our residuals should stay relatively constant across different levels of our independent variables.
Okay.
Think of it like this. If you're predicting house prices based on size, the variability in your prediction errors
Yeah.
should be similar for small houses and large houses.
Okay.
No sudden jumps or dips in the spread.
So it's like if you're baking cookies, you want them to be consistently sized, not some super tiny and some giant.
Exactly. And finally, we need to make sure our features variables are on roughly similar scales.
Okay.
Otherwise, one feature might dominate the others simply because its values are much larger.
Right. It's like comparing apples and oranges, or rather, a tiny ant and a giant elephant. Their scales are so different that it's hard to make a meaningful comparison.
A perfect analogy. So how do we actually check if our data meets all these fancy assumptions?
That's where things get hands-on.
Exactly. We need to do some detective work using plots and visualizations to see if there are any red flags.
Like a data detective searching for clues?
Precisely, we can use correlation plots to spot collinear features, those troublemakers who are too close for comfort.
And residual plots can help us see if the spread of errors is consistent or if there are any weird patterns going on.
Exactly. We can also use histograms or density plots to check if our target variable looks like a nice bell curve.
Okay, so we've got our magnifying glass and our detective hats on. But what if we find out that our data doesn't quite fit the bill? What then?
That's when we get to roll up our sleeves and get creative.
Okay.
We can transform our data to make it more linear, or we can engineer new features to capture interactions between variables.
So it's not a game over situation.
Yeah.
We can use our knowledge of linear regression to try and make the data work for us.
Exactly. But sometimes even with all our tricks, the data might be too wild for linear regression to handle.
Right.
In those cases, we might need to consider other models that are better suited for the task.
So it's about knowing the strengths and limitations of our tools and choosing the right one for the job. Well, I think that's a great place to wrap up part 1 of our deep dive.
Okay.
We've covered a lot of ground, from understanding how linear regression works to recognizing its assumptions and even getting a glimpse into the tools we can use to implement it.
Indeed. And in part 2, we'll delve even deeper into those data transformation techniques and explore how to evaluate our model's performance. Stay tuned.
Welcome back. So last time we kind of laid the groundwork, exploring how linear regression learns from data and the importance of checking those key assumptions.
It's like we got our toolbox ready and did a thorough inspection of the materials before starting the project.
A great analogy.
Yeah.
So now let's get our hands dirty with those data transformation techniques.
Okay.
We hinted at, remember, sometimes our data isn't perfectly linear,
right?
But we can nudge it in the right direction.
Okay.
With some clever tricks.
It's like when you're trying to fit a slightly misshapen piece into a puzzle.
Yes.
Sometimes you need to give it a little twist or reshape it to make it work.
Precisely. And one powerful tool in our arsenal is the Box-Cox transformation. Okay, that one sounds a bit intimidating.
Yeah.
What exactly is a Box-Cox transformation?
Don't worry, it's not as scary as it sounds.
Okay.
It's basically a way to find a mathematical makeover for our target variable.
Okay.
That helps it behave more like a normal distribution.
So we're giving our data a little spa treatment to make it more appealing to the linear regression model.
Exactly. There are a bunch of different transformations we can try, like square root logarithm or even an inverse transformation. It's all about finding the one that best fits the data.
And how do we know which transformation is the chosen one?
Right.
The sources mention something called Box-Cox tests.
Yes. These tests help us systematically evaluate different transformations.
Okay.
And pick the one that does the best job of normalizing our target variable. It's like trying on different outfits.
Yeah.
To see which one looks best for the occasion.
So we're playing stylist for our data.
I love it.
Now, even if we've transformed our target variable and our model is looking good,
we still need to address those pesky interactions between features.
Okay.
Remember, linear regression on its own doesn't consider how different features might work together to influence the outcome.
It's like assuming that the taste of a dish is simply the sum of its individual ingredients.
Yes.
Without considering how those flavors combine and interact.
That's a great way to put it, and that's where feature engineering comes in.
Okay.
Adding those missing pieces to the puzzle by creating new features that capture these interactions.
So it's about getting creative and crafting new features that tell a more complete story.
Exactly. And one way to do this is by simply combining existing features.
Okay.
For example, if we're predicting house prices, we could multiply the house size by the neighborhood quality to create a new size quality feature.
So instead of just looking at square footage and location separately, we're creating a feature that captures the synergy between them.
Precisely. Another technique is using polynomial features, which involves raising existing features to higher powers. This can help capture nonlinear relationships that a simple linear model might miss.
So for example, if the relationship between house price and distance from the city center is curved, using the square of the distance might better capture that curve.
Exactly. And remember, the goal isn't always to make the data perfectly linear.
Right.
Sometimes it's about finding a transformation or a combination of features
that
allows linear regression to capture the essential patterns.
Okay.
Even if there's some underlying complexity.
It's like finding the right lens to focus on the most important aspects of the data.
Now, what about scaling features?
Okay.
I remember we talked about how features with different scales can create problems.
Right, it's like trying to compare the weight of a feather to the weight of an elephant.
Yes.
Their scales are so different that the comparison is meaningless.
Scaling helps us level the playing field.
So it's like making sure all the players in a game are competing on a level playing field.
Right, how do we actually do that?
Yeah, how do we do that?
There are a couple of common techniques. One is standard scaling. Which centers each feature around 0 and scales it to have a standard deviation of 1.
So it's like giving all the features a standardized makeover.
Another option is min-max scaling, which squishes all the values into a range between 0 and 1.
So it's like fitting all our features into a neat little box, making sure none of them stick out too much.
Exactly. The choice of scaling technique depends on the data and the algorithm, but the key is to ensure that no single feature gets an unfair advantage simply because of its scale.
Now, all this talk about transformations and feature engineering makes linear regression seem super flexible.
Yeah.
But are there times when it's just not the right tool for the job?
You're right, it's not a magic bullet. Remember that example of predicting stock prices?
Yeah, stock markets are like wild roller coasters.
Yes.
With so many factors influencing them.
Exactly. Linear regression might struggle to capture that complexity. In those cases, we might need to consider more advanced models like neural networks. Which are better suited for handling those intricate relationships and nonlinear patterns.
So it's like choosing the right vehicle for the terrain. Sometimes you need a sturdy off-road truck instead of a sleek sports car.
Exactly. Now let's go back to those machine learning engineer interview questions.
Okay.
From the exponent guide, I found them super insightful.
They really are. They highlight those tricky concepts that often trip people up.
Yeah, remember that question about how feature scales can affect coefficient magnitudes?
Yeah, the one where we talked about how a feature with large values might have a small coefficient, making it seem unimportant.
Yes.
While a feature with small values might have a large coefficient, making it seem more important than it actually is.
Precisely. It's like judging the importance of ingredients in a recipe solely based on their quantities.
Yeah.
Without considering their potency.
Exactly. So how do we avoid falling into that trap?
The guide mentioned the T statistic as a more reliable indicator of feature importance. When scales differ, it's like a signal booster.
Okay.
That helps us separate the true signal from the noise.
So it's like having a filter that helps us see the most important features more clearly.
Another question that stood out was about how L1 and L2 regularization affect model sparsity.
Okay.
Remember how lasso regression can zero out some of the weights?
Yeah, it's like a sculptor chiseling away at the unnecessary bits.
Yes.
To create a simpler, more elegant model.
Exactly. And the question asks why L1 regularization is better at creating this sparsity. Compared to L2 regularization, the guide provided a visual explanation using contour plots, which is a pretty cool way to understand it.
Yeah, those contour plots showed how L1 regularization is like navigating a city with square blocks.
Yes.
Where you're more likely to hit a corner where a weight becomes zero.
Right.
With L2 regularization, it's like navigating a city with curved streets.
Yeah,
making it less likely to hit those 0 points.
It's a clever way to visualize how the geometry of the problem affects the outcome.
This deep dive has been a real eye-opener. We've gone beyond the basics of linear regression.
Yeah.
Explored its limitations, and even learned some tricks for bending it to our will.
And we've also gained valuable insights from those interview questions, which will not only help us ace those interviews,
For sure.
but also become more effective machine learning practitioners.
I'm ready for the final part of our journey.
Yeah.
So we've spent the last 2 parts of this deep dive getting into like all the details of linear regression.
We've learned how it works,
Yeah.
what its assumptions are, how to tweak it
Yeah.
for better performance,
Right.
and even touched on how to handle those tricky interview questions.
Now I'm thinking about our listener out there who's probably like, okay, this is all cool, but how do I actually use this stuff in the real world?
Yeah, that's a great question.
Right.
And luckily, linear regression has tons of real-world applications.
Okay, cool.
So let's say our listener is working for a company that's trying to predict customer churn. Figuring out which customers are likely to cancel their subscriptions.
Yeah.
Linear regression could be a game changer for them.
Go.
They could use it to build a model that predicts the probability of a customer churning based on factors like, their demographics, usage patterns, billing history, and so on.
So they could see if things like the length of the subscription,
Yep.
how often the customer uses the service, or their interactions with customer support, like have any bearing on whether they stick around.
Exactly. And if their data isn't perfectly linear, well, we've got that toolkit we talked about. They can transform the data, engineer new features, scale the variables, all those tricks we've been discussing to make linear regression work. It's magic.
It's like having a superpower.
It is.
That allows you to see into the future
Yeah.
and take action before it's too late.
Imagine being able to identify those at-risk customers and proactively reach out to them. Yeah.
Maybe offer them a special discount or provide personalized support.
It could make a huge difference
That could.
in customer retention
Yes,
and ultimately, boost the company's bottom line.
absolutely. And that's just one example.
Right.
Linear regression can be used for all sorts of prediction tasks.
Yeah.
From forecasting sales to estimating the value of a house.
Okay, so one thing that's been on my mind is what if we're dealing with a situation where our target variable isn't continuous but categorical?
Okay.
Like predicting whether a customer will click on an ad or not.
Right.
It's either a yes or a no.
That's a great point. And it brings us to another powerful tool in the machine learning world.
Okay.
Logistic regression.
Woo!
Remember that little note in the sources about linear regression being the basis for logistic regression?
Yeah, it's like linear regression has a close relative who specializes in these yes-no type questions.
Exactly. Logistic regression is a classification algorithm that builds upon those same linear regression foundations, but adapts it to handle categorical outcomes.
So it's like having a different lens to view the data through one that's designed for those yes-no scenarios.
It still uses a similar linear equation.
Okay.
But instead of predicting a continuous value, it predicts the probability of belonging to a particular category.
So instead of saying, this house will sell for $500,000,
Yes.
it's saying, there's a 75% chance this customer will click on the ad.
Precisely. And then it applies a threshold
Okay.
to convert that probability into a yes-no classification. For example, if the probability is above 50%,
Yeah.
we might classify it as a yes.
Okay.
And if it's below 50%,
Yeah.
we classify it as a no.
So it's still about finding those optimal weights,
It is.
but instead of like directly predicting a number,
Yes.
we're predicting the likelihood of something happening.
And here's the best part. Many of the principles and techniques we've discussed for linear regression, like feature engineering.
Yeah. Regularization and evaluating performance
Right.
also apply to logistic regression.
So the knowledge we've gained in this deep dive is like a master key
It is.
that unlocks a whole world of machine learning algorithms.
It's all connected.
Yeah.
Now, before we wrap things up, I want to leave our listener with a final thought-provoking question.
Okay. Hit me.
What if we're dealing with data that's super complex,
Okay.
with features interacting in like really intricate ways, and the relationship to our target variable is far from linear?
Ooh, that sounds like a real challenge.
It is.
What tools would we use then?
That's where we might need to venture beyond
Yeah.
the familiar territory of linear and logistic regression
Uh-huh.
and explore more advanced models like neural networks
Okay.
or support vector machines.
So it's like leveling up in the game of data science,
It is.
unlocking new skills and taking on more challenging quests.
And that's the beauty of machine learning. There's always something new to learn,
Yeah.
a new algorithm to master, a new problem to solve.
This deep dive has been an incredible journey,
It has.
from the fundamentals of linear regression
Yeah,
to its practical applications, and even a glimpse into the wider world of machine learning.
absolutely.
And I hope our listener is leaving with a sense of excitement and curiosity, ready to explore the vast and ever-evolving landscape of machine learning.
Remember, the journey of learning never truly ends. There's always a new challenge waiting around the corner, a new data set to analyze, a new algorithm to unlock. So keep exploring, keep experimenting, and most importantly, keep that passion for learning alive.